In this lecture, we're going to meet exoplanets, planets around other stars. When I started my career in astronomy in the 1980s, we knew of exactly one planetary system, our own, the one that we've been studying for the last few lectures on the work of Copernicus and others. In the year 2015, we now know of nearly 2,000 confirmed planets around more than 1,000 stars, and there are another 3,000 viable planets awaiting confirmation observations. In the last few decades, we have seen an explosion in our knowledge about how planetary systems are put together. We've gone from knowing virtually nothing 20 years ago to a nearly overwhelming diversity of data. In this lecture, we're going to look at the methods we use to discover planets around other stars, and in the following lecture, we'll talk about some of their properties and the lessons we're beginning to learn. There are two basic methods that we use to search for planets around other stars. The first of these is what might be considered the most direct method. Take a picture of a star and look to see if there are any planets orbiting around it. The other methods are called indirect methods. These are where we don't actually observe the planet directly by taking a picture of it, but rather by looking for the effects of the presence of that planet on its parent star. The first of these is to look for orbital motions or wobbling of the parent star because of the unseen planet's gravity. As we saw in previous lectures, two bodies orbit around their common center of mass. If a planet is orbiting a star, that means the star is also orbiting around the common star-planet center of mass, and its motion will be visible even if the planet is not. The other way to find a planet indirectly is if we happen to be in a favorable configuration where the planet passes between us and its parent star. When it passes between us and its planet star, it will block some of the light, causing the total starlight we observe from that star to dim ever so slightly during the time that the planet is crossing across its parent's face. We call this crossing a transit, and this transit method will turn out to be a very powerful way to find planets orbiting other stars. Let's start with the direct detection method. Direct detection has only become possible recently with the development of adaptive optics and space telescopes. These are advanced technologies that allow us to look closer and closer to the parent stars. The principal challenge of the direct detection method is the fact that stars are bright and planets are very faint. For example, planets shine primarily by reflected light in the visible part of the spectrum. If we were to look at the Earth and Sun from a long ways away, the Earth would be only about 1/billionth the brightness of the Sun. Very, very difficult to see as a consequence. Even the largest planet, Jupiter, would be very challenging to spot. Therefore, what we have to use are technologies that allow us to somehow suppress the glare of the parent star and try to see the faint planets circling around it. About 50 planets have been discovered this way to date. However, the properties of these planetary systems turn out to be special, and there are a lot of false positives with this method. It could be that a large number of these 50 apparent planetary systems discovered by direct imaging are actually not planets at all, but much larger bodies, objects that are failed stars that we refer to as brown dwarfs. These are objects that are too large to be planets, but too small for their centers to get hot enough to ignite nuclear fusion in their cores, and therefore they haven't quite made it to the state of being a star. We call these brown dwarfs because they still have a lot of internal heat, and they shine by their own light, but there's a lot of clouds and soot and other things in their atmosphere, and so people have thought originally they might be brown in appearance. Actually, we think they look kind of purple now, but back in the old days they thought they would look brown, and the name brown dwarf is stuck. However, when we weed out the brown dwarfs, there are still a few tens of planets that have been detected by direct methods. Here's an example of one of these shown on the right, the planet Beta Pictoris b surrounding the bright star Beta Pictoris, the second brightest star in the constellation of Pictor in the southern hemisphere. In this particular case, we're using a technique called coronography, in which a mask, called a coronagraphic mask, is inserted into the telescope beam and used to block the light from the parent star. Very careful imaging nearby reveals the faint planet shining by reflected light. In this particular case, we were clued in to the presence or possible presence of planets around Beta Pictoris because at infrared light and later at visible light, we could see a very, very large disk of debris, leftover material perhaps from the formation of a planetary system. We believe this may be what our sun may have looked like many billions of years ago, shortly after the sun and the planets formed, but not long enough that the debris disk, the leftover raw materials from building the planetary system, had yet to dissipate and be blown away. Often this is one way you use the direct detection method to search for planets. You look for likely places where you find these large debris disks, and then you zero in with coronagraphic or adaptive optics techniques to see if perhaps there are any planets lurking inside the debris disk. Other planetary systems have been found among relatively more mature systems that don't have debris disks. Here is a 4-planet system that was discovered originally with the Giant Keck telescope and Gemini telescopes on Mauna Kea, but here shown in a picture taken with a modern adaptive optics coronagraphic system on the Large Binocular Telescope. This works in infrared light and uses, again, a similar method of suppressing the starlight from the central bright star and being able to see now the reflected light from the individual planets that are surrounding it. In the case of HR 8799, there are 4 planets labeled B, C, D, and E. The advantage of the Large Binocular Telescope, using a new modern technique developed by astronomers at the University of Arizona, is we're getting our clearest look at the innermost of these planets, E. As we go on to talk about exoplanets, we're going to use a rather perhaps obtuse notation that was developed during the early days of discovery. The planetary system is given the catalog name of the star, in this case HR 8799. The parent star is HR 8799A, and then all of the subsequent planets that are found are labeled B, C, D, E, and so forth. It can be a little confusing because often the letters are assigned in order in which the planets were recognized. For example, B and C were found in initial reconnaissance, then D, and then E. Sometimes they're labeled for order from innermost to outermost, or brightest to faintest, and frankly, it's just a little chaotic, so you got to kind of keep your wits about you and pay attention. Direct methods are all well and good. They're the ultimate method we would like to use, but is technologically very challenging. And out of the many thousands of planet candidates we've discovered to date, only a few dozen have been able to be discovered by the direct method. All of these are very special systems. The planets are located very far away from their parent stars, out well beyond the orbits of Jupiter and Saturn in our own system, and therefore are furthest from the direct glare of the light. Future methods will be trying to work to dig deeper and deeper, closer and closer to the parent stars to find close-in systems. The other fundamental limit of these methods is it can only be used on nearby stars. The further the star gets away, the closer the stars are in angular distance to their parent stars, and the harder it is to see them, in addition to the fact that the further they are, the fainter they are. So it's a double whammy. The planets are getting fainter, and they're getting closer to their stars. So only expect this method to really only be useful for maybe the closest few planets around the closest stars, maybe within as much as 10 to 100 light years from the Earth. Other methods, the indirect methods, turn out to be a lot more powerful. One way in which these indirect methods work is it uses the property of orbits that we learned in our previous lecture on Newtonian orbits. Planets and stars orbit around each other about their common center of mass. Because the parent star is the more massive, it's going to be closer to the center of mass, and the planet, because its lower mass, is going to be further out. As a consequence, the orbital speed of the star is going to be smaller than the orbital speed of the planet in proportion to the ratio of their masses. This computer animation that I show over here on the right is for a planet around a star in a circular orbits with a planet-to-mass ratio of 1 to 50. This means that the planet is moving around 50 times faster in its orbit than the parent star about the common center of mass. However, if the planet is too faint to see and the star is too bright, or both, we wouldn't be able to see the motion of the planet or measure its Doppler shift. However, we could see the slow wobble of the parent star due to the presence of the otherwise unseen planet. How do we go about observing this wobble? One way is using direct imaging and using a method called astrometric wobble. Astrometric wobble is when we see the position of the star with respect to the background stars appear to wobble to and fro because it is moving around the common center of mass with the unseen planetary companion. This wobble is very, very small. For example, if we were to travel 18 light years away from our own solar system and look down upon the solar system from above, we would see the sun wobbling around due to the combined mass of all of the planets in the solar system. Because the two most massive planets are Jupiter and Saturn, quite frankly, those two will dominate all of the Doppler wobble, with the other planets only making small secondary contributions. But even so, the combination of Jupiter and Saturn, which have a combined mass of more than 400 times the mass of the Earth, only produce a very small wobble. At a distance of 18 light years, the total amplitude of the Sun's astrometric wobble is only about 1/1000th of an arc second. This is very tiny, just within the realm of our current technologies, but still very tiny. The picture over on the right shows what you would see if you had a 30-year mission, 18 light years away, looking back on our solar system. So you can imagine a group of very patient extraterrestrials looking down on our sun and measuring its position over the course of 30 years relative to background stars. What they would see is the sun would follow this sort of spiral wobbling pattern. This wobbling pattern is because the sun is moving around the common center of mass of the Jupiter-Saturn-Sun system, plus little secondary wiggles from everything else. It barely makes it out to 1/1000th of an arc second. This method is currently not accessible to other stars, or is only just becoming accessible with the recent launch of the Gaia satellite, which can measure the motions of nearby stars with respect to the background stars down to of order 10 microseconds precision. This should be more than enough to be able to discover planetary systems by the astrometric wobble effect, but it's going to still be many years before we've accumulated enough data to be able to find such systems. Given the amplitude here, this is 30 years of motion, it can take 5 or 10 years to accumulate enough data on wobbles to be able to detect a system like our own solar system, with giant planets located 5 or 10 astronomical units away from the parent star. A more promising method is to not measure the wobble by looking at the physical motion, physical change of position of the star with respect to background stars, but to look for the Doppler speed, the Doppler signature of that motion due to the orbital motions, using the Doppler wobble, or as it's often referred to, the radial velocity, or RV method. We've already seen the Doppler effect in the brief primer you should have watched before this lecture. Imagine now we're looking at a distant star system, S, which has a small planet, P, in its companion. I've exaggerated the mass ratio of the planet and star and shown the center of mass located outside the parent star. If I took a spectrum of the star at this location, the star where our observatory is off to the left, and the star is moving away from us, the planet's moving towards us, but we can't see the spectrum of the planet, it's too faint. But I can see the spectrum of the star. Because the star at this position on the common star-planet orbit is moving away from us, I would observe a Doppler redshift. If I waited half an orbital period later, the star is now here at position 2, and the planet has moved up half an orbit away at its position. Now, the parent star is moving towards us, and the spectral lines will appear to be blue shifted by the Doppler effect. If I watch it over time, I would see the spectral lines oscillate back and forth. First red shifted, then blue shifted, and back to red shifted as the planet and star orbit around their common center of mass. This Doppler wobble The blue shift, then red shift, then blue shift again will help me measure the orbital speed of the planet by measuring the maximum speed towards or away from me. And I can measure the period of the orbit by seeing how long it takes the star to go from red shifted to blue shifted and back to maximally red shifted again. The combination of these, put together with Newton's version of Kepler's third law, will allow me to estimate the mass of the unseen planet. The greater mass of the star makes its orbital speed very small, however, and therefore it's very challenging to measure the presence of a planet using the Doppler wobble method. Let's look at some numbers to see what we would expect. If we were looking at the solar system from a long ways away, the effect of the Doppler wobble due to the common motion of the Sun and Jupiter about their common center of mass is as follows. Jupiter has an orbital speed of 13 kilometers per second. That's pretty easy to detect. But the Sun's reflex motion about the common Sun-Jupiter center of mass is going to be smaller in proportion to the ratio of the mass of Jupiter to the mass of the Sun. Because Jupiter is 1/1000th the mass of the Sun, the apparent speed of Jupiter the apparent speed of the Sun in response to Jupiter's orbital motion will be 1,000 times smaller. 13 kilometers per second divided by 1,000 is 13 meters per second. That's about 30 miles per hour, put into everyday units. This is not outside the realm of possibility, and in fact, the technology to be able to measure speeds of about 13 meters per second has existed for the last 10 or 15 years. If we were looking for Earth-sized planets, however, the problem becomes very challenging. The Sun and Earth, again, orbit around their common Sun-Earth center of mass. The Earth has an orbital speed in its orbit of about 30 kilometers per second. Again, a speed that we can measure pretty readily with all spectral technologies available to us. However, the Sun's motion in response to the gravity of the Earth is a lot smaller. The Earth is nearly a million times smaller than the mass of the Sun. And as a consequence, the Sun's reflex motion due to the gravity of the Earth is only 10 centimeters per second, or about 0.22 miles per hour. That's the equivalent of a very slow walk. Right now, the current state of the art is speeds just starting to get less than about a meter per second, with new spectrographs on the drawing boards or in construction that it's alleged should be able to get us down to precisions of about 10 centimeters per second. That target precision was chosen precisely to be able to discover Earth-like planets in Earth-like orbits around Sun-like stars. However, we're not yet there yet, and it's probably going to be a technique not for today, but probably in the coming decade, we're going to be able to achieve this kind of precision. The Doppler wobble method had its first real success at finding a planet around a normal star in 1995. The technique is only about 20 years old. The first planet found by this technique was the star around the star 51 Pegasi. It's a Sun-like star that has a planet, a Jupiter-sized planet, orbiting around it. It was discovered by Michel Mayor and Didier Queloz of the Geneva Observatory, who were pioneers in this technique. 51 Pegasi is 40 light-years away from the Earth in the constellation of Pegasus, and Mayor and Queloz observed a periodic shift in the speed of 51 Pegasi with an orbital period of about 4.23 days, going from a blue shift to a red shift every 4¼ days. That's awfully fast. The orbital speed is 56 meters per second, which is also pretty fast compared to what our expectations are. If you use the orbital period and the orbital speed, and you use Newton's version of Kepler's third law, you can determine that this is the signature of a Doppler wobble from a 0.5 Jupiter mass planet orbiting only 5/100ths of an astronomical unit away from its parent star. This is a nearly Jupiter mass planet very, very close to its parent star. Remember that Mercury is 0.4 astronomical units away from the sun, this planet is 8 times closer to a sun-like star. This is quite a surprise, and it's a surprise we're going to say more about in the following lecture. To date, nearly 600 planets have been discovered around nearly 500 stars using the RV method. This technique is most sensitive to big planets around relatively nearby stars. Why is that? Well, first of all, the bigger the planet, the bigger the magnitude of the Doppler wobble signature. The bigger the signature, the easier it is to observe. So you're going to see those planetary systems with the biggest Doppler wobbles first, and then as your techniques refine, you will be able to see smaller and smaller speeds and thereby become sensitive to smaller and smaller planets. The reason for nearby stars is again a technological limitation. These Doppler methods don't depend upon the distance. In principle, you can see a Doppler shift due to the orbit of a planet from a very close star or a very far away star. The Doppler shift is the Doppler shift, independent of distance. However, these techniques need a lot of light. And in order to get a lot of starlight to be able to measure speeds that small, you need to use bigger and bigger telescopes, and it helps if your star is a lot closer. However, as our techniques improve and we put these highly sensitive spectrometers on bigger telescopes, we'll be able to find planets around stars further and further away. You start out with the bright and easy things, and you work your way out to the harder, faint things. The other part about this the Doppler wobble method is that its sensitivity in planets increases with the amount of time you have to observe the planet. Jupiter takes 11 years to orbit the sun. You want to really be sure you've got a planet you'd like to observe one complete orbit. So while it's relatively straightforward for current state-of-the-art Doppler techniques to be able to detect Jupiter-mass planets in Jupiter-like orbits around Sun-like stars, we would have to accumulate orbits for more than 10 years before we could be really sure we found such a system. The longer you observe, the more sensitive you start becoming to more distant planets or lower-mass planets. The current state of the art is now about a meter per second, with new spectrographs on their way that are pushing down into centimeter per second type of ranges, but it's still tens of centimeters per second. We're not quite to the point where we can measure Earths, but we're getting there. This plot on the right shows the year of discovery and the planet mass that was discovered in that year. This first planet in the late 1980s was an anomalous object that was found around a dead star. The discovery of 51 Pegasi in the year 1995 is shown over here, and all of these discoveries have been slowly building up. Notice again, these are 10 Jupiter masses, Jupiter mass, 1/10 of Jupiter mass, 1/100th of Jupiter mass, and the red line shows the mass of the Earth, 1/318th the mass of Jupiter. It's only been in the last few years that the Doppler wobble technique is starting to become sensitive to Earth-mass planets. However, these are Earth-mass planets around stars that are much smaller than the Sun. Stars that are smaller than the Sun have a lower mass, and because they have a lower mass, the Doppler wobble reflex motion is a lot bigger. We still aren't to the point that we can now find Earth-mass planets around Sun-like stars. That's going to be a problem for a different decade.